The next thing we're going to look at is transformations of functions. So the graphs of the different type of functions that we just looked at, things like x squared, x cubed, logarithms, exponentials, and trig functions, etc., those are kind of our main basic types of functions. So let's suppose we have one of those simple graphs. Let's call it y equals to f of x. We can alter them and transform them by doing operations either inside or outside of the function. For example, the effect of adding or subtracting on the inside of a function is going to create a horizontal shift. If you look at the transformation y equals f of x minus c, this is going to take the parent graph of f of x and it's going to shift it c units to the right. So every point that belonged to the original graph of y equals to f of x, which would have the order pairs x comma f of x, each of those points would be shifted c units to the right on the x-axis. If we, on the other hand, add on the inside of a function, that's going to shift the graph to the left. If we add or subtract on the outside of a function, that'll be a vertical shift. If you subtract c from f of x, that shifts the graph downward c units. If you add c on the outside of a function, that's going to move the graph up c units. We then have a couple different types of reflections. If you multiply on the outside of a function by a negative, that's going to create a reflection with respect to the x-axis. If you multiply the independent variable on the inside of the function by a negative, that will be a reflection about the y-axis. And then if you have both a inside and outside multiplication by -1, that's actually a reflection with respect to the origin. So it's important not only to know how to graph the basic functions listed above, but also how to graph any one of their various transformed versions. Let's take a look at example 4. They say for the parent function f of x equals x squared, graph each of the following. Okay. So first thing we would have to know is, what does the basic graph of x squared look like? We know that this is going to be our parabola. The vertex is at 0, 0, and it looks something like this. If we wanted to graph y equals f of x plus 2, then what that's going to do is take every single point in our parent graph, and it's going to move everything up 2 units. So essentially just going to each of the y components and adding 2 to it. The original vertex, which was at 0, 0, will now be moved up 2, so it'll be located at 0, 2. 1, 1 would have been a point on the original graph. That gets moved up 2. And it's now located at 1, 3. Similarly, we're now going to have the point -1, 3. From before, if you plug 2 into x squared, 2 squared is 4. If I move that up 3, 4 plus 3 will give us 7. So I have a point at 2, 7, and also at -2, 7. And then once you feel like you have enough points to add the detail, go ahead and graph it. So this is the graph of x squared plus 3, or as we're calling it now, f of x plus 3. And it was obtained by knowing the graph of x squared, which is the parent function, and applying a transformation, say vertical shift up by 3 units. For the next one, we're going to graph y equals f of x plus 3. This time the addition is taking place on the inside, so it's going to be a horizontal shift. Adding on the inside actually has the effect of shifting things to the left. There's going to be a horizontal shift left 3 units. Whenever you're doing a graph of x squared, or the parent function of x squared, the most important point to keep track of is, where does the vertex get moved to? The vertex, which was at 0, 0 previously, gets shifted 3 units to the left, so it's now going to occur at -3, 0. The point 1, 1 also gets shifted 3 units to the left. So that's now going to occur at negative 2, 1. We have a point at negative 4, 1. And then if you want to, you could obviously go ahead and plug some more into here. But this is what the graph should look like. This is the graph of f of x plus 3 or x plus 3 quantity squared. Let's take a look at part C. In part C, we actually have a couple transformations that are at play. We have an addition on the outside of the function. So that's going to be a vertical shift up by 2 units. And then in addition to that, we have a multiplication on the outside of a function by a negative. That's going to be a reflection with respect to the x-axis. So we would move every point up 2. Or actually, let's do the reflection first. So we're going to reflect everything across the x-axis first. I'm going to do this in steps. Let me just kind of graph what the parent function would look like. So this is the graph of x squared. When we reflect it with respect to the x-axis, we would get this. So that's the reflection portion of it. And now that we have it reflected, we have to translate and move everything up 2 units. So I'm going to take every point that's here, and I'm going to move it up 2 units. And this is what we get. This is the graph of the negative of f of x plus 2, or explicitly it's negative x squared plus 2. It's the standard parabola, but reflected about the x-axis, and then shifted up 2 units. Let's take a look at one more of these. Here we have a combination of 3 transformations. Subtracting on the inside is a horizontal shift that'll move everything to the right 4 units. We have an addition of 5 on the outside. So that's going to be a vertical shift. That's going to be up 5. And we once again have a negative multiplying out inside of the function. That's going to be a reflection with respect to the x-axis. So reflection with respect to the x-axis. To graph these, again, let's start with the parent graph of x squared. I'm just going to draw that on these axes. And let's take it in steps. So if you're thinking of kind of maybe like an order of operations approach, start with the inside. So we would first shift things to the right 4 units. So I'm going to take that parent graph, shift it to the right 4. That would move us to here. I'm now going to reflect it. That's the multiplication on the outside. This now gets reflected about the x-axis. That would bring us to here. And then the last thing we would need to do would be to take every point and move it up 5 units. So our vertex is now going to be located at the order pair 4, 5. This point here, which would have been at negative 3, 1, gets moved up 5. So that's going to be at, there's 3, negative 1, and now gets moved to 3, positive 4, because negative 1 plus 5 is 4. Same thing too, due to symmetry, this point gets moved up, and if we put it all together, this is what our graph is going to look like. So there you have it. This is the transformation of x squared. This would be the graph of the negative of x minus 4 squared plus 5. And it's obtained by a series of transformations. The next thing that we're going to get into, and this is going to be especially important as we start to get into some calculus rules later in the class, is being able to recognize a function and knowing kind of what class it belongs to. Starting off, we kind of begin your math careers by looking at some of the simplest types of functions, which are algebraic functions. What is meant by an algebraic function is it's any function that's constructed by using the 5 basic operations in math. Those 5 basic operations are addition, subtraction, multiplication, division, and the process of taking roots, so square roots, cube roots, etc. These lend itself to the polynomials, radical functions, and also rational functions. So if it's one of these basic types, it's an algebraic function. We then have trigonometric functions. These are your 6 basic ones, your sine, cosine, tangent, secant, cosecant, cotangent. And then we have a third class, which is going to be the exponential and logarithmic functions. Okay, so things like e to the x, the natural log of x, log base 2, etc. Those are exponential functions. Furthermore, classes 2 and 3 are sometimes lumped together in terms of the form transcendental functions. It's a very popular term that you'll hear referred to 2 and 3. A function is transcendental if it cannot be written as an algebraic function. So if it's not just simply adding, subtracting, multiplying, dividing, and taking roots put together, then it's a kind of a higher level of function, and we call it transcendental. We'll start off now kind of the rest of this review section. So this is chapter 1, which, again, is kind of just review for the stuff that we're going to need for our class. What we will now do is go through the remainder of this chapter and hit the highlights and review each one of these 3 main classes of functions. And we're going to start with polynomials. A polynomial is simply a collection of integer powers of x, natural number powers of x, along with real number coefficients in front. Generally, a polynomial can be written as a sub n x to the n plus a sub n minus 1 x to the n minus 1, where we write it in standard form in terms of decreasing powers of x, all the way down until we get to potentially a constant term. The highest power of x that appears in the expression, that's referred to as the degree of the polynomial, and the coefficient of that term, that number that's in front, that would be referred to as the leading coefficient. For example, the functions little f and little g that are listed here are examples of polynomial functions. This has an x to the 5th term, an x squared, and then this thing is just a constant term. And we see that the coefficients are just simply real numbers. So this is a polynomial. G of x is also a polynomial that's in factored form. If you wanted to, you could expand and distribute it all the way out and write it in standard form, but ultimately g of x will also be a polynomial as well. Things that would not be polynomials would be the functions capital F and capital G of x. Capital F of x is not a polynomial because we have a square root of x. If you recall, over in the previous example, little f was a polynomial, even though it had a square root in it, because that square root was a coefficient. The coefficients can be any real numbers, but you have to have whole number powers of x. For the same kind of reason, g of x is also not going to be a polynomial because we have x being raised to the 1/2 power. So if x has either a negative exponent or a fractional exponent, then it will not be a polynomial. One of the things that's going to be important for us is to be able to determine what's called the end behavior of the polynomial. And this discusses what the function values of the polynomial do as the independent variable x increases without bound, either positively or negatively. And this is summarized with what's called the leading coefficient test. In general, there's going to be 4 different cases here. You have 2 cases for whether the leading exponent is even or odd, and then 2 cases for whether the leading coefficient is positive or negative. Let's start with the easier case first. Let's suppose that you have a polynomial of even degree. So the highest power would be like something like x squared or x to the 4th or perhaps even x to the 100th power. Whenever your highest exponent is even, if the leading coefficient is positive, then what will happen is as x approaches negative infinity, the polynomial will approach positive infinity. We can write that kind of using arrow notation as x approaches negative infinity, f of x approaches positive infinity. Similarly, if we look at what happens as x approaches positive infinity, so as x approaches positive infinity, we see that this graph is rising up and up and up, which means that the function values are also approaching positive infinity. On the other hand, let's suppose we still have a even leading coefficient, but what if the leading even exponent, but what would happen if the leading coefficient was negative now? Well, the answer is it kind of reverses its behavior. As x approaches negative infinity, we see that the function is falling and going down, so the function values will be approaching negative infinity. So as x approaches negative infinity, the function values will also approach negative infinity. As x approaches positive infinity, as we go further and further out to the right, we see that the function values are again going down and down and down, so the f of x values are approaching negative infinity. The one thing that's kind of nice about the even case is it's consistent. It's going to either go up in both directions or down in both directions, and in that case it's determined by the leading coefficient sign. If a sum n is positive, it goes up in both directions. Sometimes people will kind of use this parenthesis notation for n behavior, up to the left and up to the right. When the leading coefficient is negative, it kind of goes down to the left and down to the right. An easy way, in my opinion, to kind of memorize this is just to have an example that's readily available to you. For example, we already said from earlier that you should have the graph of x squared memorized. The way that x squared acts in terms of its n behavior is going to be the same way that any even degree polynomial with positive coefficient will behave. It's going to go up to the left and up to the right. If you wanted to think of an example of what would happen if n is even, but if the leading coefficient was negative, easiest example would be to think of the graph of negative x squared. From what we just talked about a moment ago, you can view this as a transformation. It's going to be a reflection with respect to the x-axis. So this one's going to go down to the left and down to the right. The other case that can happen is what if we have an odd degree polynomial? And here it's going to act differently on either end. If you have an odd degree polynomial, meaning the highest power of x is an odd number, then what's going to happen is as x approaches negative infinity. So as x approaches negative infinity, what we see is that the graph is going down and down and down. Therefore, the function values f of x are going to approach negative infinity. On the other hand, as x approaches positive infinity, we see that the graph is going up and up and up. Therefore, the function values f of x will approach positive infinity. And then you can take a look at the last case. If n is odd and the leading coefficient is negative, then what's going to happen is the graph will go up to the left. So when x is approaching negative infinity, f of x itself, the function values are approaching positive infinity. And when x approaches positive infinity, the graph is going down. So as x approaches positive infinity, f of x is going to approach negative infinity. So we definitely want to know the end behavior of a polynomial. And again, if you want to kind of do it by analogy, there's nothing wrong with that. A classic example of an odd degree polynomial with positive coefficient would be something like x cubed, and that's one of the graphs that you should have memorized. We know what the graph of x cubed does. It looks something like this, going down to the left and up to the right. And similarly, if you want an example of an odd degree polynomial with a negative coefficient, think of negative x cubed. That would simply be the reflection with respect to the x-axis, and as a result, it's going to go up to the left and down to the right. So one of the things that's nice about polynomials, and what the leading coefficient test tells us, is that if you're trying to determine the end behavior of a polynomial, it's entirely determined by the leading term. So the leading term determines what happens at the infinities. These lower order terms, even though they don't affect the end behavior, what they will do is kind of impact the intercepts as well as the number of squiggles, if you will, that the graph will have in between.